Welcome back to Signal 2030, where we explore the scientific breakthroughs that are shaping our future.
Good to be with you all again. In this episode, we're excited to shed some light on an exciting new technology.
That's right. Today, we've got something pretty cool. It's about how we see the world literally through our windows.
Exactly. We're talking about windows, but not your average window. This is some seriously smart tech from KAIST. That's the Korea Advanced Institute of Science and Technology.
It's called the Reversible Electrodeposition and Electrochromic Mirror System. Bit of a mouthful, so we'll call it RECM.
RECM. Got it. And our mission today really is to unpack this. What makes these RECM windows so special? How do they actually work?
And crucially, what could they mean for you? You know, the buildings you live and work in, maybe even the car you drive. It seems simple a window, but the potential impact, it's pretty profound.
Yeah.
Energy, comfort.
Even how our cities are planned, right?
Exactly. It touches on a lot.
Okay, let's lay the groundwork. What is this RECM system, fundamentally? And, what makes it different from smart glass we might have seen before?
Right. So the core idea is that RECM uniquely combines two different electrochemical ways of working into one device.
Two ways. Most just do one thing, like tinting.
Pretty much, yeah. Most rely on just one mechanism. But RECM integrates reversible metal electrodeposition that's making a tiny metal mirror and the more familiar electrochromism, which is the color change.
Okay. A hybrid. And what does that hybrid approach actually let it do?
It gives it what they call multimodal control. So it's not just clear or dark.
Right.
It can switch between three distinct states. You've got fully transparent, like a normal window, then a colored state, kind of like tinting for privacy,
Okay.
and then a third state, a colored mirror, which they call the full block state, all controlled just by small electrical signals, low voltage.
Okay, three modes. Transparent, colored mirror. That's definitely more versatile. Now, you mentioned something really intriguing earlier, this pedestrian-friendly aspect, the anti-glare.
Yeah.
Why is that such a big deal?
Yes. This is, I think, one of the most exciting parts. Think about big cities, right? All those glass towers.
Yeah, they can be blinding sometimes, the reflections.
Exactly. Glare and light pollution. It's a real problem for people walking around or in nearby buildings. Conventional reflective windows, even smart ones, can make this worse.
So how does RECM fix that?
It's clever. It combines that reflective metallic layer, the mirror part, with an absorptive electrochromic layer, the colored part. So the mirror blocks the heat and light, but the color layer absorbs reflections before they bounce back outside.
Okay. So it doesn't just reflect everything outwards. It catches its own reflection, sort of.
Precisely. It addresses this major flaw that's actually limited how much mirror-like glass we can use in dense urban areas. It's about making the building a better neighbor, you could say.
That is smart. Thinking about the outside impact, not just the inside. So performance-wise, what did the KAIST team find? Any numbers?
Yeah, the initial lab results are pretty impressive. In that full blocking mirror mode, they measured about a 27.2 degrees Celsius temperature reduction inside compared to regular glass.
Wait, 27.2 degrees Celsius. That's enormous.
It is. Under the same solar radiation task conditions. Yeah, huge implications for cooling costs.
Wow. Okay. And the anti-glare part.
They measured a 33% reduction in the intensity of light reflected outwards compared to typical reflective windows. And maybe more importantly, they noted that visually, basically no glare was observable from the outside.
No observable glare. That's a strong claim. So 27 degrees cooler inside, way less glare outside. How does this stack up against other smart window types we know, like SPD or PDLC? What's its edge?
Good question. That 27-degree drop, you can imagine, translates directly into huge energy savings for air conditioning, cutting cooling loads, and, the carbon footprint.
Right. Big environmental benefit.
Absolutely. And compared to others, well, its main edge is that three-mode operation. SPD, that's suspended particle devices, or PDLC, polymer dispersed liquid crystals, they typically just switch between two states, usually clear and dark or clear and opaque. RECM gives you transparent, colored, and mirror. It blocks heat really well like other metallic windows, but crucially, it solves their glare problem. And it likely offers finer control than many standard electrochromic systems, too.
So versatility and solving that glare issue seem key.
Yeah.
Okay, let's dive deeper. How does it actually manage this? The hybrid mechanism, electrochromism, and that reversible metal thing. Break it down for us.
Okay, let's get under the hood. First, electrochromism. This is probably the one people are more familiar with. You apply a small voltage, and a material changes color due to a chemical reaction, a redox reaction.
Like tinting on demand.
Exactly. In RECM, this is what handles the switch from transparent to that deep blue color. That's mode 2, the privacy or colored mode.
Got it. Simple enough. Now the other part, reversible metal electrodeposition. Sounds more complex. Silver ions, you said.
Yeah, Army. It sounds fancy, but the principle is pretty neat. You have silver ions, Ag, plus dissolved in a special gel within the window. When you apply the right voltage, these ions turn into solid silver metal, plating onto one of the electrodes as a very thin, reflective film. That's your mirror.
And reversible means?
Just reverse the voltage, and the silver metal dissolves back into ions in the gel. The mirror disappears. It's like plating and unplating on demand.
Clever. So how do these two things, the color change and the mirror formation, work together to kill the glare? That's the really smart part, isn't it?
That's the synergy, yeah. It's where it gets really ingenious.
Yeah.
In mode 3, the full block state, you apply a voltage that does both things at once.
Okay.
The silver mirror forms, reflecting sunlight and heat very effectively, but at the same time, the electrochromic layer is activated, turning deep blue.
Right.
Now here's the trick. That deep blue layer is positioned so it absorbs visible light that the silver mirror reflects internally, bouncing back towards the inside of the window before that light can escape back outside.
Whoa. Yeah, let me picture that. Light comes in, hits the mirror, wants to bounce out, but it gets absorbed by the blue layer first.
You got it. So the heat and most light are reflected away, but the part that would cause visible glare outside gets trapped and absorbed. That's the pedestrian-friendly magic.
That is genuinely elegant, using one part to solve the side effect of the other. Amazing. Okay, so if it does all this, what's the actual window structure like? Is it super complicated to build? Because it has lots of layers.
Surprisingly, no. The researchers describe the structure as quite simple, which is a big plus for manufacturing. It's basically an electrochemical cell, like a sandwich.
A sandwich, okay.
You have one electrode coated with ITO, that's indium tin oxide, a transparent conductor.
Right, seen that in touch screens.
Yeah. Then comes the electrochromic gel. This is the heart of it. And on the other side, another electrode, this one modified with Prussian blue. That's basically it. ITO, gel, modified electrode.
Prussian blue.
Yeah.
Sounds familiar. What's in the gel? That's where the silver is.
Exactly. The gel contains the key ingredients. Prussian blue is a well-known electrochromic material. It goes from colorless to deep blue. It's stable, high contrast, and pretty cheap. They also add another organic salt, a viologen, which helps with the deep blue color when it's activated. And yes, crucially, the silver ions are dissolved in this gel, ready to form the mirror.
So relatively standard, well-understood components, just combined in a novel way in this gel.
That seems to be the approach, using robust, cost-effective materials in an intelligent configuration.
And making it, you said it's simpler. No complex machines.
That's another potential advantage they highlight. The process is described as simple, solution-based casting. Basically, pour the gel onto one electrode, put the other on top.
Like making, well, a sandwich.
Kind of, yeah. It avoids the need for expensive, energy-intensive vacuum deposition equipment that some other smart window technologies require. That suggests it could be cheaper and easier to scale up production.
Lower cost, easier manufacturing.
Mm-hmm.
That's always good news for new tech. Okay, let's walk through the modes again, but focusing on the voltages. How does it switch between transparent, colored, and that full block mirror?
Right, the electrochemical dynamics. Let's break it down.
Mode 1 first.
Mode 1, transparent, or the bleached state. This is the default, 0 volts applied. At 0 V, the Prussian blue and the viologen are in their colorless states, and the silver is just ions floating in the gel. Light passes through, heat comes in, good for winter heating.
Okay, standard window mode, now mode 2.
Mode 2, colored or privacy mode. Here you apply a negative voltage, specifically negative 1.6 volts relative to the counter electrode.
Minus 1.6 volts.
Yes. This triggers the electrochromic reaction. The Prussian blue changes, the viologen changes, and bang, the window turns deep blue. It blocks some light, gives you privacy, reduces glare from light passing through, but it still lets some heat through because it's mainly absorbing, not reflecting.
Got it. Privacy tint. And then mode 3, the big one.
Mode 3, colored and mirror, the full block mode. For this, you need a slightly more negative voltage, negative 2.0 volts.
Minus 2.0 volts.
At this potential, you activate both mechanisms. The electrochromic materials go blue, and the silver ions deposit onto the electrode, forming that reflective mirror layer.
The double whammy.
Exactly. So the silver mirror reflects most of the incoming sunlight and heat, giving you maximum solar energy rejection. And simultaneously, that deep blue layer is active, absorbing the internal reflections to eliminate the external glare. That's your full package. Cool, private, and glare-free outside.
Okay, that clarifies the whole process beautifully. The voltage triggers the specific combination of effects. Now, we've heard the impressive lab result, the temperature drop, the glare reduction. But what about the real world? What are the promises? And maybe more importantly, what are the unknowns, the gaps?
Moving from the lab to, a skyscraper window, the promises are clear. Huge energy savings from that thermal regulation, better occupant comfort, and solving that urban glare problem. The anti-glare aspect really is a game changer for architects dealing with light pollution regulations.
It sounds almost perfect on paper.
Yeah.
But you mentioned critical operational gaps. What information is missing for us to really know if this is ready for prime time?
Well, based on the primary research and press materials available, there are a couple of really key unknowns. First one is switching speed.
How fast it changes states.
Exactly. The press stuff uses words like instantaneous or real time, which sounds great. But the actual research papers don't give a quantitative number like, does it take 5 seconds, 30 seconds, a minute?
And why does that matter so much?
Well, think about a car sunroof. You want it to tint quickly when the sun hits, right? Or for privacy. A minute might be too long. Some competitors, like SPD, switch in 1 to 5 seconds. Other RME systems are maybe under 3 minutes. We just don't know where RECM falls precisely. It's critical info.
Okay, so speed is TBD. What else?
The other, and arguably the biggest question mark for commercial use, is durability and cycle life.
How long does it last? How many times can it switch back and forth?
Precisely. There's zero data provided in the sources about how many cycles transparent to dark to transparent these windows can handle before they start to degrade, lose performance, or fail.
And what's the benchmark? What do they need to hit?
For architectural use, you're looking for something that lasts 15, 20, maybe 25 years. That means tens of thousands, maybe hundreds of thousands of switching cycles. Without that data, it's impossible to judge long-term reliability. Its absence usually suggests it's still early days in development.
That's a huge factor. Nobody wants to replace their building's windows every few years.
Yeah.
What about power? Does it sip energy or gulp it?
Good point. It is an active technology, so it needs electricity. But the operating voltages are low. -1.6 to -2.0 volts. The crucial thing is likely bistability.
Bistability, meaning?
Meaning it should only need power to change state, not to hold a state. Once it's transparent or blue or mirrored, it should stay that way with little or no continuous power draw. It's typical for EC and RME tech.
Unlike some others.
Right. Technologies like SPD and PDLC need constant power to stay transparent. And if RECM is truly bistable, that's a major energy efficiency advantage. Probably is, but it wasn't explicitly confirmed in the sources I saw.
Okay, so potentially very energy efficient in operation, but speed and especially durability are major questions that need solid answers through more testing.
So placing RECM in the current market, how does it really compare head-to-head with the established players?
Yeah, let's line them up. It helps to see where it fits.
Okay, start with conventional electrochromics, EC, the ones that just tint.
Right. RECM versus EC. RECM's Mode 3, the mirror mode, offers much better solar heat rejection because it reflects heat, while EC mostly absorbs it, which can eventually radiate inwards. Plus, RECM has that unique built-in anti-glare feature EC lacks. And potentially simpler manufacturing could mean lower cost for RECM.
But EC has advantages too.
Sure. EC tech is more mature, its durability is better documented, and it can often achieve more neutral gray or bronze tints, whereas RECM, at least in this version, is deep blue.
Okay. What about SPD, the fast-switching one used in some cars? RECM versus SPD. The biggest difference is likely power. SPD needs constant power to be transparent. Turn the power off, and it goes dark. RECM, being likely bistable, only uses power during the switch. That's key for reducing overall energy use. RECM's mirror mode also blocks heat more effectively.
But SPD is faster.
Yes. SPD's big win is speed. 1 to 5 seconds is very quick, great for automotive needs. RECM's speed is still that question mark.
Right. And finally, PDLC, the privacy glass.
RECM versus PDLC. These are really for different jobs. PDLC is fantastic for instant privacy. It goes from clear to frosted, scattering light, but it doesn't block much light or heat.
It just makes things blurry.
Exactly. RECM is a full-on energy management system blocking light and heat, plus offering privacy. PDLC's advantages are its near-instant switching, like milliseconds, and it's mature and relatively cheap if all you need is privacy.
So looking at all that, RECM isn't just trying to be a slightly better version of the others. It seems like it's carving out its own space, doesn't it?
That's exactly the takeaway, I think. Its strategic advantage isn't just being incrementally better, it's creating a unique niche. A total solar and environmental management system.
Total management, I like that.
Yeah, because it's the only one we've seen described that handles the full solar radiation spectrum, light and heat, and deals with that critical side effect, the external glare. That human-centric, urban-friendly angle is new.
Addressing a problem others ignored or even created.
Right. And that specific value proposition, especially in cities worried about light pollution and heat islands, could absolutely justify a higher price point initially.
That makes sense. If you're solving a regulatory headache for developers or making downtown more pleasant, that's valuable. So where do you see the biggest opportunities? Where might we see RECM first, assuming they nail the durability?
The most obvious, largest market is architectural integration. Think commercial buildings first.
That makes sense.
That 27.2 degrees C temperature reduction means massive cuts in HVAC costs, which is a huge chunk of a commercial building's operating expenses. Plus, for those signature glass towers meeting strict new rules about reflections and light pollution in major cities, RECM could be the solution they need.
Makes them greener and better neighbors. What about homes?
Definitely potential in high-end residential, too. The comfort factor, the privacy without needing blinds that's appealing, and integrating it into smart home systems is a natural fit. Plus, contributing to green building certifications like LEED adds value anywhere.
Okay, buildings seem like a prime target. Anywhere else? You mentioned cars earlier.
Yeah, the future of mobility is another big one. It runs on low-voltage DC. Perfect for vehicles.
Sunroofs.
Sunroof side windows, especially in luxury cars and EVs. Reducing solar heat gain means less AC use, which saves fuel, or, more importantly for EVs, extends battery range. And instant privacy in Mode 2 is a nice feature.
I can see that.
What about trains?
Potentially, yeah. Enhancing passenger comfort on high-speed trains or planes with large windows. Similar tech is already in the Boeing 787, so the concept is proven there.
Any really niche markets, maybe?
You could get creative. Think about greenhouses. Imagine precisely controlling light and heat levels for optimal plant growth. That could boost yields, cut energy costs.
Interesting.
Or retail and museums. Protecting valuable items from light damage. Maybe even healthcare providing instant privacy for patient rooms, which is better for dignity and maybe even hygiene compared to curtains.
Lots of possibilities. So if KAIST wants to bring this to market, what's the smartest play? Go big right away.
Probably not. The smartest entry strategy is likely targeting high-profile flagship architectural projects. Maybe in cities known for tough environmental rules, like in Europe or parts of Asia or North America.
Why start there?
It lets them prove the technology in a demanding, visible setting. They can command a premium price to recoup R&D, build brand reputation, and show everyone what it can do. Solve a high-value problem for a niche market first, then broaden out. That's often the path for deep tech like this.
Okay, that makes sense. Establish the value, then scale.
Yeah.
So let's try to wrap this up. The KAIST
RECM system feels really cleverly engineered.
It really does. The elegance is taking two known principles, electrochromism and RME, and combining them synergistically to solve a problem, that external glare that nobody else was really tackling head-on with a single integrated device.
creating that human-centric, urban-friendly value.
Exactly. And the lab results on performance, the heat blocking, the glare reduction, they are genuinely compelling.
There's always a but with new tech.
There is the technology readiness level, how close it is to market. Still feels early. Those big unknowns, real-world durability, the cycle life, and the exact switching speed they need, hard numbers from rigorous long-term testing against industry standards.
Without that, it's still high potential, but also high risk for anyone looking to adopt it right now.
That's the reality, yes. Huge promise, but critical validation steps remaining.
Okay, so here's something to think about as we finish. What if our buildings didn't have to be static shields against the elements, but could actually breathe in a way, dynamically adapting to the sun hour by hour?
Not just to save energy inside, but to be, like you said, better neighbors in our crowded cities.
Yeah. Imagine walking through downtown and the skyscrapers shimmer and adjust, but they don't blind you. Imagine your car roof instantly finding the perfect tint without causing glare for the car behind.
It's a shift in thinking about building facades and glass, from passive material to active system.
Exactly. This RECM technology, if it gets fully validated, if they solve the durability puzzle, it could really redefine what a smart window is. It could shape not just our comfort, not just our energy bills.
But the whole interaction between the buildings we create and the urban environment we all share?
So the question for you, listening, is what possibilities does that spark for you? Where else could dynamically controlled light and glare make a difference? Something to ponder.
Thanks so much for joining us in this episode, and we look forward to seeing you again soon.
Bye for now.